Okay, so welcome to the seminar series on cognitive robotics offered by Queen Mary University of London. And today I'm very, very happy to have Serena Ivaldi, who is a researcher, a senior researcher, maybe she will tell us better, in INRIA in France. And I've been knowing Serena for a very long time because we actually did our PhD together in the same group in IIT, Italian Institute of Technology, a few years ago. And then Serena has been also traveling in a few places. She was a postdoc researcher in France and then in Germany, and then now she's back in France. And she's always done very interesting research at the interface between human behaviors and robot behaviors, and especially with humanoid robots. And what I like in her research is that she has always collaborated with people with different, from different backgrounds, including psychologists, and also to apply these things, like humanoid robots, in different settings, from industry to human-robot interaction in social environments. So a wide range of applications, and always doing a lot of experiments with the real robots in applied situation, which is very hard to do, and so it's I think it's always notable when this happens. And without delaying more, I give the floor to Serena. Thank you very much for joining us today.
Thank you, Lorenzo, for the introduction. So as I said, I'm an INRIA research scientist in France. It's a tenure position. I'm not yet senior, which is like the place of director of research, but who knows in the next years. And I'm also editor-in-chief of the International Journal of the Social Robotics. So this is a venue that is likely to interest most of you, especially the students. And that's it. I work in collaborative robotics technologies now, and as Lorenzo said, mostly on humanoid robots. Now that you've seen me, I'm going to switch off the camera feed because I know that the connection is a bit complicated. So sorry for the small. So do you still see my screen? Do you still see my screen?
Yes, now we do.
Okay, perfect. So so as I said, my main interest is collaborative robotics technology, and the general motivation for human-robot collaboration is that collaboration is a very complex process. It is not only a question of physical interaction and controlling the interaction forces that are developed between the human and the robot, but collaboration is really like a cognitive process. And the core of this cognitive process is the understanding of the intention, of the movement, of the goals of the human partners. And this process is really like crucial to develop collaborative robots, because it can lead to seamless collaboration, so to have very natural human-robot collaboration, like as in the same way as we could observe in humans. And then it can also lead to improving the human working condition, the human movement conditions. And it is very important to track and measure the human movement in order to build models that make predictions about the human behavior. And for doing this, one can observe many things. We can observe the human movement. It's like non-verbal behavior cues, the physical forces that arise when there is a contact or a physical interaction, and more generally, like what the human is doing or has been doing. And my main motivation is that I want to make robots that leverage all this information to help and assist the human in their daily tasks, and hopefully to improve their working condition and improve their lives. So collaboration can be very different if you see different robotics platform, and different in terms of objectives and also like application. if you think about cobots, in my point of view, from my point of view, the real use of cobots is to delegate physical tasks to the robot, and so to physically relieve the humans from strenuous tasks. In the case of exoskeletons, the level of physical assistance is really, really high. And also it's more complex because exoskeletons, as you know, are worn on the human body. What I like in this kind of platform is that in collaborative terms, they are more like there to help and not to replace the human. So they can really collaborative work with the human without, substituting the human. And it's nice because by providing physical assistance, they can really improve the ergonomy and the working condition of workers in industry. This is completely different from the case of humanoids. First, because humanoids are not yet in industry, they're still like prototypes. The way I see collaboration beyond like industrial cases, which seem to me quite far, is to collaborate as like avatars, human avatars, because humanoids can be sent to dangerous locations or remote environments, and they can act as avatars for the remote operators. And why you may think that teleoperation in this case is a form of like remote control, well, actually, it's a form of collaboration as well. It's just that they're not physically present, but in terms of like software tools and problem formulation, it's a kind of form of collaboration. And then we have mobile platforms like mobile drones with arms, etc., that I qualify generically as mobile coworkers, because it's platforms that are maybe less intuitive to interact with, but they can be very helpful in doing something that the human could never do. For example, bringing objects from one location to the other by flying or something like that. And also in this case, you can have physical interaction. So different platforms, different objectives, but at the end of the day, we are using the same mathematical tools. We are formalizing the problem in the same way and using the same control or learning tools for addressing all these situations. At least in my it's really like human-centered. So you need really to put the human at the center of the problem. So I always try to start with human observation, human behavioral study, or observing what humans do, what are their needs. And then I try to get data to have models, to understand, like to have cognitive models of motions, of behaviors, and so on, of collaboration. Then I go to the robots. As I said, robots have different objectives, but the same tools. And then I use a lot of sensors because in this like equation, having sensors like wearable sensors and also environmental sensors, if possible, can help you in having quantitative data that you can use with models to making sense of what the human is doing, of the human goals, of the human activity, of the human status, like physical status. And you can also make sense of what is the future development of human trajectories, with what we call like human intention. So in my team, we're currently doing many things, ranging from activity recognition, human movement prediction, teleoperation, exoskeleton. They all may seem far in terms of topics, but actually all these things are connected. And so I'm not going to show everything, but I want to show you like how we're using, starting from wearable devices, because wearable devices and most importantly, wearable motion tracking suits can give us information about the kinematics of the human motion. And then we use this information to build models and with machine learning tools, typically, for activity recognition and human movement prediction. And we use those for ergonomics evaluation. We use them for control and teleoperation of humanoids to improve the collaboration with the remote humanoids. And we also use them in the context of evaluation of the impact of exoskeletons on the performance of the human body in different So I will just present the work I've been doing with passive exoskeletons. We are also working on active exoskeletons. So the activity recognition and prediction tools are relevant more first is that if we want to address problems that are currently present in industry, we cannot use cameras or other like environmental sensors to monitor the human movement in industrial scenario along workstation or assembly lines, for example, like in this case. On the contrary, motion tracking suits like the Xsense that we are using here, my student went to work one day in a factory. So they're very practical because they don't require modifications or they're not invasive, let's say, and we can reliably have reliable data about the gestures and how the human is moving, the human worker is moving in the assembly lines. And of course, it's not something that every worker should use every day. But when you are in the phase of workstation optimization or training, you can use this sensor to track how the humans are behaving. And so imagine ergonomics optimization loops that aim at improving improving the gestures of the worker or improving the workstation directly. And actually what we were interested in is to have tools for automatic ergonomics evaluation starting from human motion tracking data. And we took a particular use case that comes from car manufacturing assembly lines, where workers have to perform a variety of gestures, like taking wheels and putting in the car and then do some pushing chariots with objects and so on. And usually when companies have to optimize the ergonomics for this kind of applications, they have ergonomics experts that manually annotate all the movements for the all the movements that are executed. One step that is necessary for ergonomics assessment is the attribution of weights of particular scores depending on the postures and the actions that you are doing. And so for doing this, we need to have real-time activity recognition. And so we have proposed a very simple way to do this with hidden Markov models with automatic feature selection. As you know, hidden Markov models are probabilistic models, where a state is defined by this basically set of features. And this set of features can be, for example, the height of the center of mass or the position of the center of mass in the space, the height of the hand, and so on. Usually these are defined by hand, manually assigned by experts. In our case, we decided to automatically retrieve these features by using automatic feature selection algorithm. And this works quite well because starting from recordings that we can do in industry, we can automatically find these features and run HMM, the HMM for predicting and recognizing the current activity that is performed by the humans. Of course, if you want to have a more reliable estimate, you need a bigger data set that covers many different motions for many different anthropomorphic profiles of the humans, because I mean this to counter for possible biases coming from the different anthropomorphic features of the users. And this is why in European project ANDI, where we participated, we collected a data set of human motion that is completely open. You can access it. It contains hours of recording of 13 different participants executing sequences of tasks that are typical of the car manufacturing industry, of course replicated in a lab settings. But the reason why it was done in a lab setting is that we are including many different type of sensors. So we're including the Xsense motion tracking suit, but also like qualities information, cameras information, and so on. And this is something that you can use if you want for your research, not only for activity recognition, but human movement analysis or whatever, machine learning in general. The nice feature is that it is also annotated. So you not only you have the sequences, but you have also the annotation of all the postures and the activities that is done by 3 different independent annotators with background truth. So this is quite useful. And we use this data set to improve our automatic online activity recognition. And we can basically, so starting basically just from Xsense measurement, we can recognize the posture and also the activity that is carried out by the human. Assess online if the movement and the posture the human is doing is ergonomic or not. And so we have proposed to use latent representation. So we map basically the high dimensional posture of the human into a 2-dimensional space. Of course, there is a little bit of a loss, but it provides us a tool that is very easy to understand, very visible, very legible, explainable in a sense as well, that we can use to, for example, show online to a worker to provide the feedback if the movement that the human is doing is ergonomically risky or not. Okay, so now that we have the activity recognition and the ergonomics estimation, we need to be able to anticipate future movement, because if in the future the human is going to do a very bad movement, very risky movement, we need to stop him. So the question is, how do we predict this movement? And so this is a question that is related to predictability and eligibility. So one we consider, so it is usually considered that emotion can be defined legible prediction for the observer. And we basically changed a little bit the problem formulation to match it to our application. And in our case, we to predict future movement given early observations. So we want to, so we accumulate basically observation of what the human is doing. And then based on those observations, we want to predict the future outcome of the trajectories related to the posture or whatever that is interesting for us. And for doing this, we propose to use probabilistic motion primitives, which are a very nice probabilistic, very nice tools based on probabilistic models to describe, to catch probabilistic distributions of trajectory in terms of primitives. And this is a technique that was proposed by Parastos and colleagues in a NIPS paper a few years ago that we have been using a lot in our team because it's really easy to use, easy to train. So basically you start from a small set of observation of the trajectory of the gestures or the movement that you want to be able to predict. For example, a dozen of demonstrations can be sufficient in most cases. And then starting from, so based on these observation, based on these observational demonstrations, we built basically a prior distribution from this demonstration, which in this figure is basically the blue. It's like a prior pro-MP. And then when you accumulate observations, which are the black dots, the more observations you accumulate, the more you can compute a posterior distribution that is basically a conditioning of the prior given this observation. So basically you refine your posterior distribution in time. And the more observation you get, the more your prediction is good. and you can use this prediction to predict. You can use this posterior distribution to predict the outcome of the future movement. And we have exactly been doing this with robots, with humans, with human movement, and also with robotic movements. We did it in a variety of situations, exploiting kinematics information, but also like non-verbal information or haptic information. And then we said, okay, this works. Now we try to do it with the human movement. The problem is that the human movement is high dimensional. It's not just like a force or like an angle or a Cartesian position. And if you want to use this technique in real time, you need to be very fast in computation. And so the trick that we basically exploited to have online prediction was to map the current poster, which is high dimensional, in a reduced latent space in few dimensions. Here in this figure is just 2-dimensional because I want to have a figure here that is readable. But in our paper, if you see, we usually use a latent space of a dimension 5 or 7, which is lower with respect to the 60 and more of dimensional space of the human posture that we get from the XSense. And so we compress the so when we have this mapping, we can also compress the ProMP that we learn in the high dimensional space. We can compress them in the 2-dimensional or 5-dimensional latent space. And so we have reduced, compressed latent ProMPs, and we can use these latent ProMPs for doing prediction. And so same ways as before, so in the bottom figure, you can see the black dots. The black dots are the observations that we have. And then based on this observation, we use them to condition the ProMP, and we produce the prediction of the future human posture. And this works astonishingly well. Here you can see an example of some ProMPs in the different dimensions of the latent space for different tasks. And then on the right, you can see some example of predictions giving 30% of observation of the movements. And so in one on the red, and so the red skeleton and the black skeleton are the ground truth, and the red is the prediction. It's more than because we can estimate if the movement is going to be risky, and the error that we have in this latent representation reconstruction, it's very small. It's acceptable. Okay, so now that we have a technique for doing prediction, let's see how we can use this for the control of robots, for anticipatory control. For exploiting this prediction, which is tele-operation. And as I said, tele-operation may seem something far from collaboration, but actually it's a pretty good form of collaboration. The robot and the operator are not physically in the same space. I mean, it's not meant to be like that. But the operator is sending signals, is sending commands, is moving, and the robot is trying to match the operators, is trying to collaborate in a sense with the operator. And so for me, this is a form of collaboration. And then of course, if the robot is doing some task with the human partner, there is another form of collaboration that is mixing. But okay. And so if you think about tele-operation, there are two types of operators that are in the equation. One is the operator that is doing ground control, that is basically very far from the robotic setting, from the scene, and is just basically sending very high-level commands to the robot. But we can also, like another level of operator, which is the operator that is really controlling the robot body with motion retargeting. And as you can see, like in the top video, basically with XSense, we capture the human posture, the human movement, and we retarget this on the robot. And we can do it for like very simple movement. We can also do it in a like remote setting where basically the human is really not doesn't see what the robot is doing, but is seeing what the robot sees, like with his eyes. So this can be also done. What do we need to include the prediction? But the first ingredient what we need is to have a human-aware controller. So we need a robot controller that doesn't only think about the robot status, but also includes information about the human and the goal of the human and what the human wants to do. And so in the past, we have the first way we addressed this problem, human-aware controller, was when we did the Codico. Codico was a European project. The Codico project final demo that was about a human-aware controller that was basically formulated as a human controller that was reasoning with the robot dynamics, but also the human dynamics, and it was also considering the contacts with the environment and the contacts between the human and the robot. So this controller was meant to control just the human just the robot, of course, because the human is not controllable. But in the problem formulation, it was including the information coming from the human dynamics estimation, and also it was considering the contacts between the human and the robot. That's why in this specific experiment, the controller basically activates once the human is taking hold of the robot's arms and there is a physical contact. So this was okay, but we didn't manage at that time to include the intention prediction. It was not clear how to do it. And then we figured out that one way to do it was to work on the whole body control. So a generic way to see a whole body controller is to see it as a QP, quadratic programming culture problem, where you try to minimize a combination of several tasks that have a certain weight or a priority, subject to number of not infinite, but number of many different equations that include the robot status, the joint velocities, the positions, the constraints, and so on, the contact equations, the same that we mentioned before. And of course, you can formulate with the robot equation, the human constraints, robot constraints. That's using a combination of many different tasks that are expressing basically the trajectories. You can imagine to put this prediction inside one or more of those trajectories. And so this is exactly what we try to do. We try to do something like this with the whole body controller that we proposed with the Otani and Buyarmani in INRIA, where we had a whole body controller that, again, similar to what we did before, was considering an augmented state where it that had the human state variables and also the robot state variables, and of course it was just controlling the robot, but in real time it was taking the information from the XN suit to feed this to the human state representation. And the same, we basically included the human trajectories in the desired task that we had to include in the whole body controller. Okay, so we know that we have to put the prediction part in one of these tasks. We don't know where yet, but imagining the desired task, the desired center of mass, desired trajectory of the hand if you're doing something together with the robot, and so on. Now, the question for tele-operation is a bit more complex because when you are differently from what we did before, that was basically replicating the experiment in simulation. We didn't have a real robot to control. If we want to use the same technique for controlling a real robot in tele-operation, you really need to have a whole body controller that is robust, like a robust in a sort of italic sense, robust and can handle a variety of different motions. This is like the most crucial part for having a whole body controller for tele-operation, because you don't know in advance what the operator is going to do. So unless you have a very precise sequence of tasks and gestures, you cannot imagine to have a controller that is only capable to do just a bunch of tasks and is not optimized to take care of, to handle many different tasks. And a crucial point here is that you need to have an optimized controller that cannot be end-tuned. Otherwise, it's not really, I mean, in our experience, it was really impossible to rely on an end-tuned controller that was tuned for a bunch of, for a small set of motions and that was working on all of the motions. So what we proposed in this sense and was to optimize automatically the structure and the parameters of the controller so that the robot could perform a variety of motions, and that we could have like a controller that was able to do the very different motions of the operation. And so to do this, basically we defined all the possible tasks that we had to put in the whole body controller, that can be neck, torso, left arm, or whatever, center of mass, and so on. We defined all the possible parameters for these controllers, and then we used a multi-objective optimization tool to minimize different metrics on a simulated robot that was supposed to perform a variety of tasks provided in a sequence. And look, I don't know if you are like familiar with multi-objective optimization, but the output of a multi-objective optimization process is not one single solution. It is a family of Pareto optimal solutions that are basically those in the figure that you see on the right in green or blue. And basically those are all the families of possible solutions that minimize the different objectives that you have. And so you can choose in these families of Pareto optimal solution basically by selecting if you want to promote one or the other objective. Of course, this is in 2D because always for readability, but you can have 3 or more objectives. And so once you do this and you have your Pareto optimal solutions, basically you can try these solutions on the real robot and see what are those that are like working well on the robot. And this is exactly what we did. Now we are trying also to automatize this process. But now basically your operator does first movement and you don't really care because the robot can handle all these kind of movements. And on the left, you can see basically the results of the optimization and like basically the frequency of the task and their level, their task level in the stack for whole body control, the whole body control, which basically gives you an indication of a kind of default generic formulation for the whole body controller. And so once you have this, you can use this controller for teleoperation. So you can use it to teleoperate the robot for doing different tasks. So here in this video, the robot is completely teleoperated. There is no knowledge of the sequence. The human can do whatever he wants to do. So here is opening a door, and then he's going to take some objects. So yes, here the robot lost a bit of. So here you can see it can also take objects, and this is interesting because I don't know if you're familiar with whole body control, but this task of bending, like doing almost a squat in a weight, even if for ACAB it's not a big of a weight because it doesn't have a big payload. But this is a task that is like in terms of whole body control is very complicated for its balance and stability. Whereas opening the door while you're standing, it's a task, it's a manipulation task that you can also do well, almost without endangering the balance. So these are tasks that usually, if you were taking a task specific, like an activity specific approach, you would do with 2 different controllers. And in this case, we are doing everything with a single controller. Yeah, that's it. Okay, so now that we have a nice controller that we can use for doing many things, we can add the prediction part. So unfortunately, I cannot give you a lot of details on this part because it's something that we are currently submitting. But since I already told you, explained how we do the prediction, you can easily guess. So basically now we have a good controller. We know how to predict using motion primitives and observations. So basically, what are we doing is that we are taking observations from the operator with or without delay with respect to robot, because the two are separated in principle. And then starting from observation, the robot builds a prediction of what the human wants to do. And then it computes accordingly the predictive movement, and then is able to introduce this in the whole body controller. And this runs smoothly. So this is our current one of our current experiments of teleoperation. So we are also introducing delays between the human operator and the robot, and artificially introducing delay. So you can see that the human is moving, and basically whenever the robot figures out what the human wants to do, then he executes the it includes this information in the whole body controller. Okay, this is kind of operation, and we are also doing this now with the Talos. We recently we acquired the Talos before the lockdown in March last year, so we haven't made a lot of progress with that, but we are confident we will try to do it, even if we don't have access to the lab as usual. But we are trying to port also this on the Talos, because we would like to do collaboration experiments with more physical assistance that ICAP cannot give. And so finally, I want to arrive to the point of exoskeletons. So exoskeletons, in my view, are sort of humanoid robot, can be sort of seen humanoid robot, sort of, not, it's not a humanoid robot. But if you include them on a human model, then it becomes a humanoid, like a digital human model, which is assimilated to the humanoid in a sense with the exoskeleton. And so at the end, we use the same tools at the end. In my lab, we're currently working on I heard my echo. Working on passive and active exoskeletons. So I don't have a lot of information to share right now about active exoskeletons, but we are targeting upper body exoskeletons that can give assistance in like physical. Done some work in passive exoskeletons, in particular with the Autobot PAEXO exoskeleton in the context of the European project ANDI. And recently, we have started to use exoskeleton in hospital settings to help our colleagues in the ICU working on the thread during COVID. And we have made a pilot project to study the feasibility of using exoskeletons in the ICU. So I'm going to try to be very quick on this, because so it's important to notice for this validation is that at the end, wearable sensors, all these sensors are really very important, because if you want to measure the impact, the benefit of the physiological or biomechanical impact of the exoskeletons on the human body, you need many sensors. So look at these experiments. Basically, the human is equipped, is standing on a force plate, so we're measuring X-sense sensors. So we have inertial motion tracking. We have a VO2 mask for measuring the metabolic consumption of energy, and so many tools. And it's important to notice that in this case, since the physical interaction between the device and the human, so the exoskeleton is worn on you, so you cannot only use exclusively objective measure, you also have to complete basically objective measure with subjective measure. So you have to ask people how they feel using the exoskeleton. So you can, from sensor, retrieve the physical benefit if there is, But it's important that people also give you a feedback if they really feel good in the exoskeleton, if the subjective perception matches the quantitative observation of physical benefit. And this is exactly what we did. So basically, we in our trials we compared basically the task with and without the exoskeletons. So the green is in this plot is with exoskeleton, and the orange is without the exoskeleton. It's not exoskeleton. And basically, we compare the in terms of oxygen consumption, the muscle activation and movement duration, center of pressure displacement, because there could be also like an effect on the balance, and in that case, there was not. But we tried to see if there was like if those quantitative observations were coherent with subjective observation that we retrieve with the NASA TELIC score questionnaire and also other like interviews and self-reports. And I think the nice things in this study, beside the validation of the exoskeleton, is that we developed really like I think a good methodology to study these platforms. And this was very helpful last year because in March I was contacted by some doctors in the ICU of our hospital because they were really struggling with COVID patients. And one of the operations that it's very critical in patient care in the ICU is the prone positioning. So patients that are mechanically ventilated, that are intubated, they have to be turned upside down regularly to increase the oxygenation. And as you can see in this operation, they are frequently bent. It's very physically stressing. And so we ended up providing them with exoskeletons. So we conducted in April a pilot study in an hospital simulation center with the mannequin. Then we so where we compare different exoskeletons, we selected a good candidate that was Laevo, and this was used in the ICU by 2 volunteers. In October, with the second wave, we also gave them 2 additional new Laevos. And since there are basically they have been used non-stop since October. In total, more than 60 different people have used the exoskeletons, which I think it's a success. Even if they are passive and they're not yet active, but there are good reasons for not having active in this case. Think that we observed after a while in January we switched because it was complicated from the organizational point of view. So I'm going to give you a little bit of details on how we did it, because in case you have contacts with your local hospitals, maybe you can share this information and try to help them in doing the same. It's not very difficult, and we are sharing all the methods we use to facilitate the replication. So to give you some information, it's 15% of patients with the COVID need to be in the ICU, like have acute respiratory distress syndrome, and they require ventilator support. And this operation of prone position is used to improve oxygenation. So this is how it is done. So the patient is in the ICU. This is a mannequin. It's not a real patient. And these are pictures that we took to illustrate like how it's done. In this picture, you see 3 doctors, but actually in real conditions, the operation is performed by a team from 5 to 10 doctors, depending on the patient's weight, essentially, and needs, because patients can be in different forms of life support. So basically, the patient has to be put on one side of the bed. The doctor that is behind the head is holding the patient's head, because there is a risk of extubation. And then we have to turn the patient on the bed and reposition pillows and check cables, life support, and so on. So this is like an example to show how you can do it with a mannequin. And during this operation, you also change the bed sheets and so on. And basically, during all these operations, there is a problem, is that from the postural point of view, the the physicians are strongly bent, and in particular, so the physicians that are on the lateral side of the bed are bent or strongly bent. Their posture is changing a lot, so at the end they don't have a huge benefit in using exoskeleton. This is basically what we found. But the doctor that is positioned behind the head of the patient is basically standing in a strongly bent position for 3-4 minutes. And if you do this operation like once per day, it's not a problem. But if you do it like 10 or more times in a row, this becomes a real problem. And like even very young physicians have a lot of back pain at the end of the day. So we want to try to help them. So as you can see, the doctor that is like behind the head of the patient can be strongly bent. This angle of being bent depends a lot on the height of the physician, the position of the bed, and you could say, hi, why don't you raise the height of the bed? But the problem is that you have eight physicians around the patient. They don't all have the same height. Some are small, some are very tall, and so they find a compromise, and this compromise often doesn't work for everybody. So you need to help them. And so we used some, we took some experiment, we did some experiments to basically track the angle of inclination of the back to see if this operation was really like stressful for the back, and it was. We compared 4 different solutions to find a good match, good candidate for the use in ICU. We compared Core 4, which is basically a very easy, simple device based on elastic bands. LiEvo and BECX, which are 2 passive exoskeletons that basically have a very similar distribution of the assistance. And then Cray-X, which is an active exoskeleton. Using the Xsense, we did a kinematic analysis to see if there was a change in the way the people were doing the gesture with and without the exoskeleton. In this case, it was very important that there was no change in the way the gesture was performed, because you don't want them to change the practice, the medical practice. And basically, we compared we did a comparison of the kinematic analysis with the subjective perception of the users in using these elements in terms of many criteria. I'm not reporting everything, but most importantly was the perception of physical assistance and the ease of installation. This is very, very crucial. To physical benefits of the presence of skeleton on the body. So we track many different muscles and also measured EKG to see the effect. And we performed also a torque analysis with our simulated humanoid, so a simulated digital human model, using a whole body controller. So basically reusing the things that we have developed for humanoids. We use many questionnaires to track the use in the ICU. So, well, at the end, the good news is that it's a device that can help. It's considered to be very useful at the patient side. So we have regular users that whenever they have to do a positioning, they use the exoskeleton without a doubt. But in terms of organization in the hospital, it's clear that it cannot be a shared tool. It's more like an individual device because there is the problem of fitting the exoskeleton to your body. This is an operation that takes time, and the physician don't have time to do this fitting every time. So yeah, we should buy many more for more the physicians. So this is good because now we are moving, we are continuing this collaboration with the hospital also to test the feasibility of exoskeletons also in healthcare task. And then just a call for action. If you are collaborating with your local hospital and you want to know more about what we did and how you can help them, please contact us. And I've put online all the supplementary material, everything that you need to use to replicate our study. And if you want to help them also just in deploying the exoskeleton without further like tests or experiments, I mean, we can help. We are currently helping another hospital in Paris to do the same, and the physicians are very happy about that. So I think that's it. So about these 3 activities, for the first part, we're trying to produce toolbox that we will probably share hopefully in the next month or after the end of the ND project. We will try to improve also the tele-operation. Hopefully, if the paper is our paper is accepted, you will hear more about that, about how we use the prediction. And then we are basically taking the results for the first 2 studies to pour them in the active exoskeleton. So that's it for me. Thanks to also my collaborators, because I'm not alone, of course, in doing this. I have great colleagues and PhD students. And but that's it. If you have questions, I would be happy to answer.
Yeah, thanks a lot, Serena. I think it was amazing. A lot of interesting stuff, and especially the last part. I think for me was really interesting. I'm very pleased to see that you could use this to help with the COVID emergency, especially because I guess your research didn't start with that objective in mind. By tools that you have developed for a certain purpose, then you could redirect them to something that, of course, was unexpected. But I think it is very interesting, and it shows what is, I mean, one of the real values of research, which is, you develop interesting tools, and then you may use them in applications that you didn't even think about before. So I think it's
exactly.
It's quite amazing.
If you look at the timeline, so what is the timeline? Timeline. In this case, this is a very pertinent comment. It's like a political comment. So I was contacted end of March, and basically in 2 weeks they had an exoskeleton. Imagine doing this with call for projects and the usual pipeline of projects recruiting people.
Yeah, no, I have to say that even in the UK there were like calls for let's say quick response. But I think it's interesting that you had already research that was ready to use, right? Because otherwise it would have been impossible to develop these solutions without having already the research done. But the research done previously was maybe for another purpose, but it's interesting to see how it could be redirected. So
yeah,
I think it's quite good. Maybe you can switch back on your camera if you want. There were some tech problems during the presentation, but I think most of it was good and we could hear. There is a question on the chat. It's a technical question. Maybe I will read it. Then Ivan can specify if I do any mistake. But it was about having more details about the automatic feature selection for the HMM activity recognizer. What technique do you use for the automatic feature selection, and what features?
So in the paper we use 2, and at the end we use the wrapper method. Okay. I don't know if this answers, but it's very it's not something new. We use the very classical state-of-the-art technique.
Okay.
Sorry, what was the name of the method again?
Wrapper method. Wrapper.
Wrapper.
Yeah, I will write it in the chat.
Okay, thank you.
I'm writing this in the chat.
Thanks. Okay. Oh, wrapper. Okay, yeah. Yeah, sorry, I haven't heard of it. Can you suggest a reference?
So maybe where is the paper? I don't know if I added the reference to the. So the paper is in it's activity recognition. It's very easy. Activity recognition with automatic feature selection, and it is in RAL. It's in my web page, and here you can find the reference. I think we use the HMM Learn. It's a Python library for HMM, and the code is online, by the way. So there is a link to the GitHub page where we have the code as well, in case you want to really see the details, because I know how these things work.
Yep, thank you.
There's
What's
also
the
like
yeah.
it's this one in RAL, activity recognition with the automatic feature selection.
No, I see I can't see the year when it was published.
2009, I think.
2009, right? Thank you.
19, yeah.
Yeah. It was, yes, 2019.
2019, yeah. Okay, yeah, I have a general question actually about the predictions. When you do so you said, okay, I like this approach with the, let's say, a probabilistic method. So you have a certain prior, and then when you do the prediction, you incorporate observations to update your posterior. Do you need to have observation on the full input space, or can you have partial observations? Either in this one or in general, also in the other, like with the HMM. So do you need to observe the full, let's say, vector of data, or can you have partial observations? So what happens if you cannot observe some of the variables?
But in this case, in the case of FlowMP, once you define the state that constitutes the ProMP, then you need to have observations that match this. I think since it's probabilistic, you could imagine to like add some filtering probably to compensate for missing data, but we haven't done yet.
Okay, yeah, because my question then is even, let's say, maybe a bit more general. So you show how you collected a lot of data from the human movements, typically using the Xsense suite. Yeah. Then when you want to use this for predictions, I think it will be very cool if you could do, let's say, if you could predict the movements without seeing all the data, right?
Yeah, that would be nice. Yeah, we haven't done that.
Okay.
No,
okay.
we were just because this would be like more relevant for camera, like when you have occlusions, and so at some point the data are missing. But for the moment, we are just making the assumption that we have the Xsense. The Xsense is always giving us the skeleton, and so we don't have this problem. But one thing you can do, because in the case of human movement prediction, which is this case, we map the posture to a latent space.
Right.
And so since we're not predicting, so to reconstruct the movement, then we use the autoencoder feature to reconstruct views probably. In the case of in the entire posture, we always use the entire posture. But for example, from the Xsense, you can extract the trajectory of a joint or like an end effector of a particular point of interest. You don't have necessarily to predict the entire posture. You can use it in many different ways. For the tele-operation, for example, we don't predict the entire posture. We take specific, for example, the center of mass or the hands.
Right. And I think you're cutting off a bit at the moment.
I am there.
Okay, yeah. Yeah, maybe I missed the very last part of the answer, but I got the idea. So the other thing I wanted to ask is whether so with the Xsense, you measure the kinematics, basically. And I think maybe in something that you show later on, you were measuring also the forces, some of the interaction forces. What do you, so for what do you think is the relevance of measuring the interaction forces, and what kind of forces do you measure at the moment?
So for example, in this application, so if you see in the human, we had the XSense. So the XSense gives you the kinematics information, and the interaction forces were giving us the interaction forces, like the force plates at the feet and the interaction forces at the level of the hands. Basically, they allowed us to compute the dynamics of the human. And this computation is done to basically be able to write the human dynamics equation. And the estimation in this case, basically you do it in the same way we do the estimation of the ICAP dynamics, with the same principle, which is you have a graph representation of the kinematics. So graphical representation of the robot, like the rigid body representation, you can propagate the kinematics information, and you can propagate as well the forces information across the structure. And in this specific study, we were using the dynamics estimation of the human is done with the in a probabilistic fashion. And it was not my work; it was the work of Claudia Latella in IIT. That worked with Francesco Nori. So Francesco will tell you about that.
Yeah.
But in principle, like the intuition behind this is doing the same estimation as we did for ICAB.
Okay, I see. So the only forces that you are measuring on the human side is on the feet.
Feet and also the hands, because you have the ICAB has 4 torque sensor.
Okay, so you use the ICAB as a sensor for the human as well. Okay.
Exactly.
Yeah, okay. I see. I think I don't see any more questions in the chat. Maybe I wanted to ask another one. In the beginning, you showed at some point to the visualization of the ergonomics, let's say. So you said we visualize this we create a 2D, this one, a 2D representation that is legible, right? Which I guess, for example, the red will be bad ergonomics and the green good ergonomics, or something like that, right?
Yes.
So you said that this is legible, which I agree, and then you said it's also explainable. Do you mean by that the system will also tell you why that posture is not ergonomic and how to correct it, or?
Yes, in some cases, yes. Actually, here I would have to go into the details of how we train this latent space. But this is a very simplified representation of the posture. But when you train this latent space, you can train it in different ways. Works. There is a sort of distinction. So there are areas in the latent space that corresponds to certain posture or certain type of actions, like actions where you're crouched or where you're sitting. I don't have the photo here, the figure, but if you look at the thesis, the PhD thesis of Adrien, the one of Adrien Malzeta was my student, in his PhD manuscript, which is in French, but the figures are, easy to find. There is a part where he really visualized that the bottom part of this latent space, it's often it's basically dedicated to motions where you're moving legs a lot, when, for example, you are crouching or lying strongly bent or something like that, whereas other parts are more related to upper body movements, or so in a sense there's way to explain. It's not that easy. I think maybe I've been too optimistic in say explainable, but I think there are ways to match this, maybe with rule-based methods, to try to give explanation about what the system is doing. There could be in any case.
And also to recommend.
Yes.
Because I think ideally it would be great if this could be used also to recommend the modifications in the movement, right?
So if you see, in the video, when you're moving, you are creating trajectories. in this latent space. So so it's like a game. So you can sort of say, okay, if you want to do this kind of task, try to avoid the yellow part, or try to stay in the green part, or something like that. Because there is a trajectory, you can plot pro-MPs on this space. And so something that we couldn't finish in this thesis because it was finishing, but we had started to have pro-MPs in this space, as we did for the post recognition, to have also the prediction of if the movement was going to be wrong. So this is something that we have to, so we will provide the code for that in a few months, hopefully, because it's something that we have to do for the demo of the European project. So hopefully it will be okay.
Yeah, it sounds very interesting. And in addition, you mentioned that one important aspect is to then get feedback from users when they use, for example, the exoskeleton, right?
Yes.
I was wondering, for this kind of works on ergonomics, whether you could get also feedback from practitioners, like from a physiotherapist or something like that.
Yes, we didn't have this so far, at least for the for the Autobook, for the work with the Paxo, no. We do have where it is. Yeah, so for the work with Paxo, no, but in our European project we have an ergonomics expert that is in a German company, and we are collaborating with other industrial partners that are like very active in this kind of sense, but we didn't have collaboration with physicians. We mostly collaborated with the ergonomics experts that are in the companies.
Okay,
yeah, and for the hospital, not yet.
Okay. Okay, yeah. I think there are no more questions, but I think it was amazing and nice to see in your presentation a lot of different robots. I think you have now a big family of robots in the lab.
Yeah.
And it was also nice to see some cool dancing by the iCub.
Yeah.
The robots are having fun as well.
My favorite right now are the tele-operation experiment. Dancing is what it is. It's here. Dancing, I mean, I would have never thought about doing dancing. I have to give credit to Luke. Do things on the robot. So that's why sometimes you see, like the robot here, the hand was kind of broken. At some point, you see a piece of hand that is that is going out. Yeah. So,
I think these whole body tele-operation, they're quite amazing. Okay, so thanks for this, Serena. I will close the talk here. Thank you very much for being with us, and surely I think people enjoyed, and surely many will watch the recordings later. So thanks a lot, and good to see you.
Well, thank you for the invitation and for the questions.